To understand the architecture of the traditional internet, you have to look at its physical footprint. Every web page, database, and software application relies on corporate-owned data centers to process and store information. Cryptographic networks operate as an interconnected mesh of devices spread across the globe, functioning entirely without central infrastructure. These systems secure and transfer billions of dollars in value without routing through a payment processor, a central bank, or an authoritative directory. Decentralization, trustlessness, and censorship resistance are the mechanical outcomes of peer-to-peer networking. The central technical problem of this architecture is coordination. Millions of individual computers must maintain a shared, secure reality without any central authority to mediate the conversation. To see how they accomplish this, we will build a peer-to-peer network from first principles, starting with a single node and scaling up to global blockchain synchronization. Understanding blockchain requires moving past the concept of a center to learn how data routes directly between equals. The fundamental building block of any decentralized network is the individual node. In this system, a node acts as a peer, representing a structural deviation from the legacy internet, where roles are fixed. On a peer-to-peer network, every device possesses dual capability. It is simultaneously a client requesting information and a server providing it. Look at this dynamic. A single digital node splits into two active halves, acting as a consumer pulling data inward and a provider pushing data outward at exactly the same time. This collapse of consumer and provider into a single entity is the prerequisite mechanical constraint for all distributed cryptographic systems. We can observe why this matters by comparing the standard client-server architecture directly against the peer-to-peer mesh. This split-screen flowchart illustrates the baseline data flow of both models. On the left, the client-server architecture routes all communication through a central hub. The client-server side has an inherent scalability bottleneck. Adding users increases the load on the central hub until it reaches capacity. Because all data flows through that single point, if the central server goes offline, the network fails. The peer-to-peer mesh utilizes a resource inversion. Because every peer provides services, adding users adds bandwidth, compute, and storage to the collective. This creates fault tolerance. When individual participants disconnect, active data streams reroute through adjacent nodes, allowing information to continue moving. The ownership models are opposed. Central servers require a trusted operator to dictate access, while the peer-to-peer mesh is ownerless. The peer-to-peer architecture removes the fragility and centralized control vectors that make client-server models incompatible with decentralized finance. This structural independence introduces a paradox. How does a new, isolated computer find the network if there is no central directory? The solution is a process called bootstrapping. The network software contains hard-coded entry points, known as DNS seeds, reliable nodes maintained by the community. The isolated node signals a bootstrap node located at one of these known addresses to ask for the current state of the network. This triggers a peer exchange. The bootstrap node returns a list of active network IPs, which the new node uses to build a localized map of adjacent peers. The new node establishes direct bilateral connections with these discovered peers and integrates into the mesh. This expansion is iterative. Newly connected peers pass along their own address lists, causing the node's connection lines to spiderweb outward and expand its routing table. Networks like Ethereum utilize distributed hash tables to execute this routing process efficiently without relying on centralized indexes. This organic discovery process ensures the network remains resistant to censorship, as there is no central registry to shut down. Once the physical connections are established, we can examine how data moves across them. The BitTorrent file sharing protocol serves as the mechanical precedent. The foundational concept is distribution through fragmentation, where a massive file is broken into small, manageable blocks. This diagram illustrates a digital swarm. A file divided into 4 blocks is scattered across 4 participating nodes, meaning no single participant holds the complete file. Data transfer relies on parallelism. A node increases its download speed by requesting different pieces of data from multiple sources at the same time. As it downloads missing pieces, the receiving node immediately pushes the blocks it already owns outward to other peers. This swarm mechanic, where the active consumption fuels wider distribution, provides the architectural blueprint for how blockchains synchronize global ledgers. We can map these swarm mechanics directly onto blockchain architecture by replacing file blocks with financial transactions and ledger blocks. We can trace the routing of a new transaction broadcast, starting at the individual user level. This network map shows a broadcast beginning. A single user's wallet generates a new distinct transaction data packet. The transaction travels to immediate peers, which act as independent auditors to check the data against protocol rules before validating it. This initiates the gossip protocol. Validated data is duplicated and pushed by those nodes to all of their connected peers. The transaction ripples outward concentrically until the entire global network possesses the data in a matter of seconds. From there, block propagation begins. A miner bundles a group of these gossiped transactions into a new, cryptographically validated block. The miner uses this same gossip mesh to broadcast the finalized block back out to the network, updating the shared ledger globally. Notice that no single node dictated the history. The updated record emerged from overlapping independent validations passing through the mesh. This gossip mechanism allows a single piece of data to become global knowledge, providing the raw material for the network to reach a shared conclusion. Consider a final thought experiment. Attempt to map Bitcoin's ledger onto a traditional client-server architecture. This matrix isolates systemic vulnerabilities across two dimensions: control and single points of failure. Under a centralized model, whoever owns the server owns the ledger. They retain the authority to freeze accounts, reverse transactions, and censor users. Housing a cryptographic ledger on a central server recreates a traditional bank, removing the primary value of the technology. On the peer-to-peer mesh, censorship or data alteration requires successfully compromising thousands of independent nodes simultaneously. The architectural layout of a peer-to-peer network creates the specific technical constraints required for trustlessness and censorship resistance. But removing the central authority creates a lingering mathematical challenge. If thousands of uncoordinated computers receive conflicting data, how do they agree on the exact same history? Solving that problem requires understanding distributed systems and the advanced mathematics required to achieve global consensus across a chaotic network. We will explore those mechanics in the next module.